Hi, and welcome to this week's episode of the Structural Engineering Podcast with Max and Zach.
I'm Ted Goldstein, worked as a structural engineer in New York for about 8 years, and then about 2 years ago, moved to Japan, sort of taking in all the structure here, had a spark of inspiration of how we could make things a little more efficient in the States.
As you just heard, this episode we're talking with Ted, the inventor of a clever new blind bolt alternative that we think is a worthwhile item to have in your design toolkit. We also get into some of the differences in Japanese and American structural engineering, which could probably fill a whole episode alone. Before we get started, one public service announcement. AISC is looking to reduce the number of steel sections we use and have available to us. The origin of the giant list we have at our fingertips is a kind of thrown together group of shapes that manufacturers across the country were rolling in the 1920s, and it's due for some cleaning. If you use RAM, you may have seen this memo pop up. Why ask engineers and not fabricators who know exactly how much of what they're producing? Well, for one, steel gets used in places that aren't buildings. And two, I doubt all that many people will submit anyway, so you might as well make sure your favorite W10 bracing beam makes it into the future. To participate, simply print out some steel takeoffs and send them to Alan Adams at Bentley, so ALLEN.ADAMS at bentley.com. Now on to the episode.
Tell us a little bit about your product. Maybe give us a little bit of intro about it. We'll start there.
Yeah, so the Shuriken Structural Nut Keeper is a way that you can bolt what you used to have to weld. And it's targeted specifically at HSS splices. So, in the US, we don't use HSS for columns very much. And that's, unfortunate because they're lighter and thus have less embodied carbon than a wide flange column does. But splicing in HSS is difficult because you can't use standard high strength bolts, at least not until now. And so you have to either do a lot of field welding, or you need to use proprietary blind bolts, which are quite expensive. And that's really limited the use of HSS in the States. So the goal of Shuriken is to change that by letting you make a bolted splice. And the way it does that, I've actually been thinking about how to describe it for an audio-only audience. It's a bit tough geometrically, but basically it has a plastic cup that holds the nut in place on the interior, on the inaccessible side of a bolt hole. And that red plastic cup is held in place by a steel ring that gets tack welded in the case of an HSS splice, to the splice plate, which stays on the interior of the column. And then both the steel plate and the plastic cup have teeth that interlock, so the nut can't turn. And that means when you insert the bolt from the exterior and you go ahead and put either the impact wrench or a torque wrench on it, you can apply the full torque required to pre-tension, even A490 bolts, and the nut will stay static on the inside. And you can do now fully pretensioned or slip critical bolted connections with standard bolts, even when you can't get to the backside. So
very cool.
I think it's an exciting development.
Yeah, absolutely. I've got a sample here that you sent over, and I think it's just a really cool, extremely simple way to solve an issue. It seems very obvious when you're holding it that it's a great solution.
Yeah, this is actually about version probably 10 or 12. Each time I thought, wow, I think I just had a great idea, and then about 3 days later, oh no, that won't work. And that cycle went around quite a few times before I ended up here.
Bet. Where did the first innovation come from? Where did you see the need for this, basically? I see the benefit now, but what was the spark?
Yeah, so, unfortunately, Japan has a great engineering industry that's well established. They don't really need foreign engineers the way some other countries do. So as an engineer from the States who had only the choppiest of Japanese, I couldn't realistically work as an engineer here. So I was, taking classes during the day, just trying to learn the language and walking past a lot of construction sites. And here in Japan, basically every column, with the exception of maybe like a canopy on a rail platform or something, every column is a tube, whether that's HSS or, in the case of high rises, a built-up box. And I saw that and thought that was, that's really great. We should do that in the States. And I sort of thought through the reasons why we don't. And really the one that was harder to address than any other was the splices. Because even if you can make the connections relatively simple, which you can, in the end, if you still need to make a field welded full penetration splice, you're not going to get much uptake in the engineering or the fabrication community. And for good reason. Making full penetration field welded splices stinks. So I started to think about how you could, get a nut basically to stay put so you could put a bolt in from the inside. I had once worked on a project in Florida where we had a big HSS transfer girder, and it was sitting on a seated connection, and in our drawings we had called for them to weld it to the seat. And the fabricator said, well, can I just weld a nut to the inside? I said, well, that's a pretty good idea. And you're not really supposed to weld nuts from a code standpoint, right? Because it affects the heat treat. But in this case, right, it's a seated connection. So all the bolt was doing was making sure it didn't slide off the seat. So we said, okay, yeah, go ahead and do that. So that was sort of the thing that got me thinking, okay, well, you can't weld it, but what if you could fabricate something with like plates and bars to prevent it from turning and, hold it in place? That gets a little complex. So I started to think, okay, maybe it's a cast solution where you have some sort of metal cup that gets cast to restrain it, and then that sort of worked, but there were some issues, and casting is expensive. So eventually, dealing with all those issues, we ended up at this solution, which is one plastic piece, which is very cheap to make, and one stamped metal piece where they basically, they start with a strip of sheet steel and they use a hydraulic press to sort of pop these out, do the cutting and the bending all at once. So yeah, that's how we got here.
What was it like trying to learn this whole manufacturing process to figure out, all of this? As engineers, we have code books and we can kind of, track through a design, but going to make a whole product, what was that like?
Yeah, I have no doubt that a person who was experienced in manufacturing and supply chain management and all that would probably already be selling these. It's a learning curve like any new thing. I've got a manufacturer in Maryland that is making the plastic pieces and assembling it, and it worked out that we're actually making the metal piece in China and shipping it over, but that was not really the goal in the beginning. And I'm sure if I had that requisite experience from the get-go, I wouldn't have found myself in that situation. But that's okay. We're gonna onshore the metal portion production after a batch or two, and we'll be okay. But it's definitely been an interesting learning curve. It bears no relation to engineering.
So what are the inherent issues in an HSS column splice?
Yeah, so we talked about that a little already. Basically, the most problematic issue is you can't get your hand on the inside. And that's why we use wide flanges, really, is because you can just use two hands and bolt it. So once you're one-sided, you have a few options. You can do a welded splice. You can do, blind bolts, hollow bolt being the most common. But that really adds a lot of cost to projects. And and in the end, really everything comes down to cost, right? So you can use hollow bolts, which are not too bad to put in the field, but they're about $20 a piece for a 3/4 inch hollow bolt, as compared to $1 for a 3/4 inch nut and bolt, right? So it's a huge difference. You can also do end plates or some other exterior attachment that lets you use normal bolts, but now you've made the column bigger. And, from the perspective of the architect, that's square footage. That's, has an effect on the quality of the space. And that then becomes money at some future date too, right? In terms of what you can rent it for and all that. So, everything is money in the end. Yep. And, just whichever method you choose, you're definitely incurring some costs somewhere along the line until now.
And you mentioned Japan, HSS is kind of the standard. Well, we use wide flanges. What is the typical connection in Japan? Is it always a moment frame? So they're welding at each floor, not doing do they bolt splice, or is it more typically they're just going to be a welded splice?
Yeah, so I think we could easily do a whole episode on comparative structural engineering. But yeah, they use HSS columns almost exclusively, certainly in buildings, or if the loads get too large for HSS, they'll go to built-up boxes. But typically every girder and every beam is moment connected, to every column at every floor. So there's a huge amount of welding associated with that because their moment connections are all through plates.
Mm-hmm.
So just to give a sense of what that means, if you have, say, a 3-story column, in the States, the fabricator would just cut that column to length. Maybe it's 45 feet, and they'd weld on the shear tabs or whatever other connections they need. In Japan, that 3-story column is going to have 2 through plates, for the 2 flanges of the beams at every floor. So the first thing they're going to do is they're going to cut it into 7 pieces in the shop. And then they're going to put the through plates in and weld it all back into one piece. Sometimes, which is just astonishing to me, if you have beams of different depths framing into the column, now you need 3 through plates at every floor so that you have, one to connect each flange to. And so the first thing you do when you get that column in the shop is you cut it into 10 pieces. It's crazy from the standpoint, of an American structural engineer. And then, so once they've done that, they put the through plates through, and they actually weld stubs for all the beams and then do a bolted beam splice in the field, essentially. And then, the splice of the column itself is always a full penetration field weld all around. And, when they set it up, it's not like you can hang a column from a crane while you're waiting for a guy to do this labor-intensive weld. So when they come to the field, they've actually got plates sort of sticking out from each side on both the top and the bottom column, and then they bolt them together, for a temporary erection connection before they weld it. So in addition to all the welding, you've got this temporary connection, which itself has 16 bolts and 16 plates, and then they burn it off afterwards. So the amount of fabrication really just blew my mind.
Wow.
And, that goes again, I guess, back to the spark, right? It's like, wow, it'd be great to use HSS, but no one is going to do this.
Yeah.
Just for reference, is Japan a high seismic region?
It is the high seismic region. Yeah.
Awesome.
Basically of anywhere in the world. I think in terms of both frequency and intensity, Japan is just about the most seismic place you can get. I mean, just like, it's pretty incredible. On a regular basis, once a week or so, you'll just sort of feel the buildings moving a little. It's not, now after 2 years, I've sort of gotten used to it. But definitely, when I first got here and you're just sort of hanging around, as a person from New York, I don't know what an earthquake really feels like. It's like, oh, it's moving. Does that mean it's about to start moving a lot? But, it's so far it's been okay. But it's definitely something to get used to.
Yeah, it was pretty crazy. I think it was last year. This is way off topic, but my sister was in Japan and they were going through, I think it was a typhoon while also an earthquake at the exact same time.
Oh, I remember it.
I was like, that's absolutely absurd that these buildings are undergoing both loading conditions simultaneously.
Max
and I
thought about it from a standpoint of lateral load, but you're right.
Yeah. Thought that was pretty cool. What type of work did you do when you worked in New York? What sort of structural engineering?
Yeah, so for 4 years or so, I worked at a company called GMS, and they do a lot of private sector work. So commercial, including fit outs and new construction, and then also a fair amount of residential. So that was a fair amount of two-way concrete slabs, that sort of thing. And then for 4 years after that, I worked at a company called STV, which is sort of a totally different clientele. They did a lot of work for New York City Transit, the other sort of regional rail agencies in the New York area, aviation, and, other sort of institutional clients. So it was nice. I sort of got to see, both ends of the engineering world. And it's quite different. I mean, the steel is the same, concrete is the same, but the structure of the clients that you're working with is totally different, and the expectations are also quite different.
Yeah, I can imagine.
I bet the timelines on projects are too.
Yes, at one they're short and stable, and at the other they're long and extendable.
So does the Shuriken require any ESR report, or in what way has it been tested?
It's a great question. So as far as the ESR report, it's a question we get pretty often, and the condensed answer is no, because you don't need it, but we're going to do it anyway. So the first half, no, you don't need it. Basically, Shuriken is a wrench. It's a disposable wrench. You put it around the nut, it stays in place. But the same way, if you patented some new handheld wrench with, I don't know, a wavy handle, you wouldn't need to get that approved, right? It's just a wrench, and it doesn't prevent you from complying with the RCSC specification to a T. And so the shuriken is the same way. It's just holding the nut there. It's preventing it from turning like any other wrench. And you can install connections with standard hardware, following all the requirements in terms of procedure, tensioning methods, and all that. So it's okay to use as is. But with that said, it's a question that comes up a lot. And, engineers have time constraints like anyone else. And to expect them to, listen to that explanation or seek that explanation and think about it is, just one more thing to ask. So just from a marketing perspective, it's good to have that report just so that instead of giving this explanation, I can say, yes. So that's the plan. We'll go ahead and do that. And then as far as testing that's already been done, so I mentioned the first production batch is underway, but we had a batch of a few hundred made beforehand, and some of those were sent to a fabricator in California, and that fabricator put together some test specimens, and we were looking to do, verify four things really. So one is it robust enough? If I put an A490 bolt in there and, fully pre-tension it, is the shuriken strong enough to resist that torque? Two was, how does it handle misalignment? And that's really key. That was one of the things that drove all this iteration in the design, was handling misalignment. So basically we made a specimen, we, shifted it all the way to one edge of the bolt hole, we installed the shurikens, and then we shifted it the other way before installing the bolts. So basically you could barely get the bolts in the hole, which is, the worst case you're going to get in the field, and had them install the bolts that way. And then the third thing we wanted to test was just different configurations of hardware, washers, and tensioning methods. So we did the turn of nut method, the calibrated wrench method, and the DTI washer method, which are three of the four pre-tensioning methods that you find in the RCSC specification. The fourth one is twist off, but obviously that doesn't apply here. And the other thing we wanted to test was washers, because usually you don't need a washer under the nut within the shuriken. But in the rare case where you're doing a pre-tensioned or slip-critical A490 bolt using A36 steel, you need a washer. So we wanted to test that configuration as well. So that was all the technical stuff to do with shuriken itself. And then we also had them build a splice mock-up. I think it was a HSS 10 by 10 by 3/8, and just to make sure that from a practical standpoint, the joint that we're suggesting is easy to assemble. And that went, very smoothly. So with that was enough to get us going, and we're gonna have it on sale soon. But as I say, going forward, we'll definitely plan to get that ESR or some similar certification, perhaps from RCSC directly, just to give people that warm, fuzzy feeling of, official approval.
Yeah, I could absolutely see the reason to not need one, but it is kind of our habit to say, "Oh, a new product. Let's look up, see its testing." So
that's what I did when I was a structural engineer. So I don't blame anyone.
So what sizes are available, and are there any limits to steel grade?
Yeah, so currently the only available size is 3/4. I'm just getting moving, and wanted to make sure that there's enough interest and demand, because of course, for the manufacturing, the most expensive part is the tool to actually make the piece. So right now the 3/4 are, in production. And as long as things go well, and it seems like they are, we've had a fair amount of interest up to this point, we'll go to bigger sizes. Definitely want to do 7/8 and 1 inch, because those are common bolt diameters. It's common that a project is all 3/4 or all 7/8. You rarely see a project that's all 1 inch, but often, if the contractor has some real heavy connections, they'll use 3/4 inch A325s for the small stuff, and then 1 inch A490s for the big stuff. And they want that separation so they don't get confused on site. So it'd be good to accommodate them with that too. And then bolts get bigger. You can go all the way up to 1.5 in the book, but whether or not we go past an inch, I think, is going to depend on demand, because the bigger you get, the more expensive it is to make it, and the fewer you're going to sell. So at what point it doesn't become worth it anymore, we'll have to see. But yeah, definitely 3/4, 7/8, and 1 inch. And then as far as grades of steel, do you mean the substrate material that you're joining, or the grade of the bolt?
Grade of the bolt, I mean.
Yeah, and then in terms of bolt grades, you can use it with A325 or A490. And we've tested it with both. There is actually, in the manual, there's this Group C bolts, which are even higher strength than A490s. They were added with the 15th edition? Yeah, the 15th edition manual. Those are only available in larger sizes and not very commonly used in the US anyway, so we're ignoring those for the time being.
Cool. So, I mean, you already touched on this, but fit up failure and mistakes while erection and stuff, like what there's tolerance built into this, so if it's misplaced, I assume the bolt and the actual, like, the shuriken, the plastic piece can move around a little bit. Can they bend at all while trying to be placed? Do they have to be tack welded on all sides? And then, what is the recourse if there is an issue? What are the odds of an issue?
Sure. Oh, there's a lot to unpack there.
Yeah, sorry.
Let's see. So I'll take the easy one first. Do you have to tack weld it on all sides? We say to tack weld it at all 4 corners. I suspect that from a practical standpoint, if you just did 2 opposite corners, you would be okay. But officially, you should do all 4 corners, because if you only do 2, it could flex a little. As far as the misalignment in general, that was one of the hardest things that really drove the development of this. And, if for anyone listening, if they've seen it, or maybe if you're at a computer, you can go to tubularconnect.com, and there's an image right there on the homepage. But the metal portion has these tabs which are flexible. And while they hold the cup from rotating, hold the nut from rotating, and keep it tight against the plate, they're flexible in the lateral direction. So the cup and the nut can move laterally to accept a bolt that's off center. So it's designed so that if you can get the bolt in the hole, you'll get it into the shuriken. There's no situation where you get the bolt through the holes and then you can't join it with the nut. That's really the whole key to the design. If you're misaligned to the point where you can't get the bolt in the hole, definitely there are some options, but I think that's a more general question than a shuriken question. Certainly you could weld a plate on the outside, but sometimes you got to bring it back to the shop. That's the case with any connection where you can't get the bolts in.
Beyond HSS column splices, where could designers use this?
Yes, so there are a few other applications that I've thought of. Obviously, extending HSS, you can go to box columns that are built up a plate. And I think, in infrastructure projects where loads are often a lot higher than what we see in buildings, you see a lot of box members, whether they're truss cords or, just columns in infrastructure. And those would definitely be applicable, because right now they actually already bolt a lot of those, but generally there's going to be some hole in the box so a guy can stick his hand in and tighten the bolts, and then you need to have either a hatch or weld a closure plate in there. And so it would be a time saver in terms of labor to be able to just bring the member in, bolt it up, and be done. The application that I'm really the most excited about, I'll call it our stretch goal, is speed core. I don't know if you guys are familiar with speed core. It's like,
oh yeah,
anyone
it's the
who
coolest. Come on.
Yeah, anyone who gets the AISC newsletter knows it's the hot new thing, right?
Yeah.
And it's an awesome system. There's no doubt about it. It's way better than traditional reinforced concrete cores, but it requires a huge amount of field welding. I mean, if you've seen, I think the best known project is probably the Rainier Square project. And there they detailed it to avoid full penetration welds, but they still had to weld for the full capacity of the plate using, I think, like a groove weld and then a fillet weld on top, right? And that's a lot of field labor, and is worth it because it speeds up the project by X months. And obviously to the owner, that's a huge benefit in terms of cost. But if you could transition from welding all those seams to bolting them, that would, I think, would accelerate things even more. Oh, yeah. And we could call it speedier core. But, the reason you can't bolt it now is you've got all these cross ties that go between the interior and the exterior face, that go between the plates on the interior and the exterior of the wall. So you can't get a person down there, at least not safely, to stick the bolt through so someone can tighten it. But with this, what you could do is you could essentially prepare some strips in the shop, make a pair of them, one that would go on the inside that would be lined with shuriken, one on the outside that just has the holes. And then you could make a bolted splice in double shear for speed core. So I don't want to call that our white whale, because if I recall, the whale won, but that is the big target. That would be very cool if we could, get this into use in speed core and speed it up even more.
Oh yeah, that's an excellent goal. I would call it white whale. It could be a different. It ends differently this time.
Okay,
you get the
sequel. And then beyond that, one thing I've heard from fabricators that we've spoken to is just sort of, wow, these will come in handy. There's all sorts of complex connections where because you don't really have space or access to get your hand in there, you weld it either in the shop or in the field. And so I think this is going to come in handy a lot for those situations. It's just sort of hard to imagine, from whole cloth what that might look like. Because when we imagine a hypothetical building, it's nice and perfect. Right, exactly. Everything's orthogonal, everything's at the same level. So what those connections will look like, we'll just sort of have to see. And, I think it's one of those things, you've probably had this experience where you look at a set of shop drawings and the fabricator is suggesting to do something differently than you designed it. And you go, wow, that is really smart. I never would have thought of that. And I'm sure that'll happen here. I'm sure there are applications that, despite the fact that I've obviously been thinking about this a lot, just haven't even crossed my mind. So it'll be interesting to see what they come up with.
Absolutely. I mean, yeah, erectors, fabricators are just absolute craftsmen in what they can put together, and it always blows my mind. I kind of tie into my earlier question on erection issues, if there are any or whatnot. What has the response been from erectors and fabricators? Any hesitance there, or they're pretty excited about it?
Yeah, I've definitely gotten some good responses. I mean, of course, as I say, we're not quite on sale yet, at least as of the recording of this episode. So I haven't had a huge amount of feedback, but the ones I have spoken to are definitely interested in it. And already they've come up with some ways of using it that I hadn't thought of. I'd say as far as concerns go, one thing that was brought up was that sometimes for large projects, fabricators will fabricate the material way in advance, a month or two in advance, because they want to make sure that they are not the source of the delay, no matter what happens, right? So they'll fabricate it and then they have to store it. And you got all these huge pieces. Where do you store it? You put it outside, right? So if you're using shuriken, at least if it's a very big piece, if it's maybe a small splice plate for a column, you could just put it in a box, right? But if you're talking about big pieces that have shuriken on them, they're going to be outside. And so there was a question of how you address that weathering issue. Fortunately, unlike twist-off bolts, which are very sensitive to lubrication and can't be relubricated by the contractor, hex bolts or A325 bolts with a standard nut can. So we told them basically, if it's going to be outside, wrap it in plastic. Put a garbage bag over it or use one of those industrial-sized saran wraps, just to keep it from getting directly wet. And then, if it's going to be out there for a long time, maybe put some, non-water soluble lubricant on the nut, just to keep it from getting a lot of water. But fortunately, as I say, with A325, the contractor is allowed to go in there and apply some lubricant to make sure they're tightening properly.
Absolutely. I saw on your website that you have a galvanized option, and maybe I'm just sort of missing. Is that an application where you might want to use a galvanized plate? Because I know there's some welding concerns with galvanized, and then you would have to re-galvanize. Where is that application?
Yeah, so if you're doing something that is exterior, let's say a canopy, and it's galvanized, the plate for shuriken is not structural. And if it were to rust away, it would just fall off into the tube. No one would ever see it. It doesn't carry any load, so it doesn't really matter. The only possible issue would be, if you have dissimilar metals, the one is it higher or lower on the galvanic series? The one that's more corrodable is always going to corrode on behalf of the entire structure, right? But in the case of galvanized things, the zinc is more corrodable, right? So the presence of the shuriken would ever so slightly increase the rate of corrosion of the galvanized. Now, the surface areas of these shuriken versus the surface area of a whole hot-dip galvanized canopy is tiny. So it should be a trivial effect. But if a client is insistent on, some really long design life, or just, out of a desire for sort of a belt and suspenders approach, there's nothing to stop us from just going ahead and hot dip galvanizing the shuriken plate as well. And yeah, you would want to touch up the tack welds, but again, what's the surface area of that tack weld versus the surface area of the whole structure? At that point, I think even the most conservative
You're cutting hairs at that point. Yeah,
that's right. But we say it's a special order just because all the plates are fabricated, of course, out of just mild steel. So if you want it galvanized, we need to just go ahead and send that off to a galvanizer. It adds a little bit of time and a little bit of cost, but it's certainly something we can do. I project to have it on sale in late October of 2020, and I think there's a fair amount of slack built in there, so we should be able to hit that date, but somewhere around there. And once it's on sale, the lead time is whatever FedEx ground takes to ship it, 2 to 5 business days, I think. A lot of proprietary fasteners, if you go, for example, to Lindapter's website, you can't order a hollow bolt, right? You get funneled to a distributor who does the actual sales. And I think it's worth noting, all these fastener companies, they have all these catalogs and websites, it's all aimed at engineers, and they're all devoid of prices, right? Because
Always.
They don't want the engineer to know what it costs. But just for the sake of simplicity, we're doing this as, a basic e-commerce sort of system. So if you like the product, just go to the website, go to store, put it in your shopping cart and check out. And you'll have it in 2 to 5 business days.
All right. That's faster than anything else is going to arrive. So no delays there.
Yeah.
So you mentioned Japan has been successful in using HSS columns more typically for steel structures. What techniques or detailing do they use to make this possible? And I think we've hit that one too.
Yeah, I kind of jumped this one early.
Well, I will just say one other interesting thing about that is, whereas here we make moment connections by putting flange plates on the column, and then the beam in the field is the full length of the beam. In Japan, they install a stub that's usually 2 to 3 feet long off the column in the shop. And then they make a splice in double shear of the beam in the field. And it has a lot of interesting effects, because one of the things you can do that's pretty cool is if you make the stub a little bit stronger than the beam, you can essentially bring the seismic fuse, the weak point, out to where that splice is. And so here we do, reduced beam sections, RBS connections in high seismic areas to make sure that that yield point is off away from the face of the column. But if you install a nice beefy beam stub in the shop and then do a connection in the field to a beam that has slightly less capacity than the stub, that's a really effective way of pushing the yield point away from the column. And that was something I wanted to sort of toy around with when the idea for shuriken started to bubble up. So it never really got anywhere. But
Yeah, I mean, it's almost like a side plate system, right? You're bringing that stiffness out farther into this. You get a stiffer moment frame. I didn't realize that was kind of Japan's technique for a lot of structures. I think it's really smart and redundant and, nice to just make the whole system a moment frame where you can, if more columns are part of that system.
Yeah, and just as an aside, when I was somewhat more bored before this whole thing started getting wheels, I drew up some typical details of how they put this stuff together. So I'll send you the drawing.
Cool.
It might be interesting to look at.
Yeah, absolutely. That would be great.
Is the typical construction there steel, or is it concrete, or is there mixtures or masonry? What kind of systems are you seeing when you're walking down the street?
Yeah, so masonry is almost unseen. You may see it in some older buildings, but in current construction practice, I mean, just off the top of my head, I can't remember seeing any masonry. And no surprise, right? I don't know what the highest R value you can get out of a masonry system is, but it's certainly not terribly high. You do see a lot of concrete and steel. I don't know the exact ratio, but it could be 50-50. But whereas in the US, any tall building is going to have a concrete shear wall, at least if it's not speed core, right? They very rarely use concrete shear walls here past about maybe 5 stories, because my understanding, although I haven't spoken to Japanese structural engineers to verify this, is that it's viewed as somewhat unpredictable, the behavior of the concrete shear wall, and they prefer moment frames, whether they're the steel moment frame that we talked about with all the through plates or concrete moment frames for taller buildings. And it's really surprising to me, right? Because for us, having anything above, I don't know, what do you think, maybe 15 or 20 stories without a shear wall is just
it's unheard of.
Surprising, right?
Yeah.
But here, you look at construction even of 40-story and taller towers, and it's just steel moment frame the whole way up. The columns are big, built-up plate boxes.
Yep. Are they
And
concrete
again,
composite core? Like, do they fill the boxes with concrete ever?
I think it happens, but I don't think it's regular. But
Okay.
I don't want to
Yeah.
give you an authoritative answer there. But yes, so even for a 40-story building, it's all steel, box columns, moment connected to every beam at every level. And I know where things get quite tall, they also work in dampers. So they will put dampers into the structure the same way that we put braces in a brace frame. And that takes a lot of the energy out. And you do see brace frames, but they also typically only get used on relatively shorter structures. So like you'll see parking garages here where it's maybe a 5 or 6 story parking garage, and every single bay on the exterior is a brace frame.
Going a little overboard.
Brace frames, we're used to having maybe one, or if the architect is nice, we get 2 bays, right?
Yeah.
And
right.
We're happy. But here it just runs the whole length of the building because the seismic loads are huge.
That's awesome.
And I think a lot of that is just because both the shear wall and the brace frame, they're so stiff that, if you do that for anything that's more than, a relatively short, relatively light building, the loads just get enormous. So by letting it move a little with a moment frame, you can get it down into a range that you can handle.
Is there a BRB option in Japan still? I know that like originally that idea might have come from Japan, but do you have that beyond shipping it from Utah?
I haven't seen anything where I go, oh, that's a BRB, because here you would expect to see, okay, I have a big single plate connection, and then there's a steel pipe around it, and the plate and the pipe aren't connected to each other, right? That's sort of the signature of a BRB. I haven't seen anything here that fits that exactly, but that doesn't mean they don't do something similar in a slightly different configuration.
Yeah.
Now, we were talking to the U.S. Resiliency Council, and they brought up Japan as talking about how everyone there is very aware of earthquakes, aware of resiliency, and they drive that. That's a big push in Japan that buildings need to go through these earthquakes consistently. And in the U.S., we design buildings to be torn down after a big seismic event. Sounds like Japan, it's a very common thing to do this of moment frames and stuff. Have you noticed that at all in the culture? I mean, looking at buildings where brace frames are on every face of every bay, that's mind-boggling. That kind of, to me,
Yeah,
talks to that.
Yeah, absolutely. There's a difference in philosophy. The expectation here is that you're going to be able to go back into your building after even a major seismic event. I don't know if that means you're going to be able to go back that day. Presumably, they're going to do inspections, but it's not like in the States where, as you say, the expectation is if it's a major event, you prevent loss of life and then you build a new building.
Yeah.
And I think that's just the reality of being somewhere where earthquakes are so frequent. If you were tearing down tons of buildings after every significant earthquake, you would never be able to build anything new beyond just replacing those. So I think it's not so much a philosophical difference. It's just sort of the practical result of being somewhere where earthquakes are so common.
We did, I don't know what episode it would have been, but we had looked into Japan's seismic code, and that it's almost this two-stage sort of analysis where the high-frequency earthquakes, much like we would just look at wind, must remain in an elastic range, and then the extreme events where we look at, what's an earthquake, 2% in 50 year, like something more equivalent to that is where it is allowed to dip into that plastic. But for a huge spectrum, you're safe.
And just, I guess, actually to add one more note to the question about, really driving home resiliency and earthquake safety and all that. My son is 3 years old. He goes to daycare. And even there, they do earthquake drills. And there have been, one day I had to pick him up at the park nearby instead of at the school because they had done an earthquake drill where they go to the park. And it's very cute. They have, you can't put a hard hat on a 3-year-old, right? But they have these little padded bonnets that they put on all the children. So it's like all these children wearing pillows on their head, running around the park waiting for their parents to come pick them up. But it's from the time you're very little, it's driven home, what to do as far as just, getting away from windows, opening doors, so that you don't get locked in, basically. All of the furniture here that we have has posts going up to the ceilings to keep it from falling down in an earthquake. Just things that you wouldn't really think about in the States, or at least in most of the states, are just, sort of common practice here.
Wow, that's fun.
Okay, so Max and I talk about this a lot, not really on the show, but we text each other all the time as we're traveling through the country of check out this connection, look at this system. How do you think this worked? Our minds are always going, right? We're always looking at the ceiling in every building, trying to look at the structure. As a structural engineer going from the United States to Japan, what are the biggest differences or the things that jump out to you the most beyond the, tube steel columns?
That's interesting. That is definitely number one. Aside from that, I guess just in general, we tend to fabricate joints in the shop and then, create the actual joint in the field by, connecting to whether it's a shear tab or, again, flange plates, something like that. But in Japan, they tend to fabricate the joint in the shop and then splice the member in the field. So it's not just moment frames, but also brace frames. You'll see layouts where you have not exactly a gusset, but a plate welded to maybe the horizontal in a brace frame and a stub coming out from that for the diagonal. And then in the field, they'll bring in just a straight piece that's the diagonal, and they'll splice it to those stubs. And that just seems to be, I'm not sure that either approach is inherently better, that you could prove either way to be better, but that's just sort of how it's done here. So that's been sort of interesting. Also, with architecturally exposed stuff, you do see a fair amount of mostly tubes, just because that's what they use, that's exposed. And, in the States, when we do AESS, we generally require that all the welds be ground down to be basically invisible and be painted. So you get this sort of continuous, unblemished member. And here they just don't really care. You'll see the seam from the weld. You'll even see where the erection tabs were and had been burned off. They just leave them there. And, I got to say, no one cares.
Yeah.
I mean, I'm a structural engineer. My eye, I'm attuned to notice it much more than the average person. I don't care. I think in the States, we've just sort of, because it's something that we in the construction industry notice, we assume it's important to the aesthetics of the structure. And I think in practice, no one really, the architect sees it. And so it's very important to them. They notice it. But to an average person walking through, say an airport with some big, interesting, branching tube column, they don't care if there are some little circles around them and some tabs sticking off. So I think that's maybe one thing we could learn. And just, you were talking about how you're always taking photos. I, too, am always sort of, I have to imagine that people think I'm a little odd because, I'll be standing in a crowded rail station concourse with my camera pointed up at the ceiling. And it's not like you're in Grand Central and it's like some beautiful mosaic or something. It's just a ceiling. There's just beams and stuff, taking pictures. But I've got, at this point, a pretty extensive album on Google Photos of Japanese structures. So I'd be happy to share that with you guys, and you can scroll through and see if anything looks interesting to you.
If you follow our Instagram at all, you've probably seen a lot of these in the last couple of weeks. Ted's got a good eye for photography.
Well, cool. I think that's all the questions I got. Thanks for spending your morning with us.
This has been great. I really appreciate it.
Hey guys, thanks again for listening to the episode. Let us know if you have any questions by reaching out to us on LinkedIn, Facebook, Instagram, or email. You can also find these links and more information about the specific episode in the show notes below. Have a great week.